So section 10.5 is going to kind of complete our transition to doing things instead of by hand, to doing them on a calculator or a computer. One thing that I've already done is I've already uploaded some matrices. So I put this thing in matrix I, and that's called the identity matrix for reasons that I'll explain in a little bit. The identity matrix. And I put that in my calculator in matrix C. And then I have two other matrices, A and B. Now, one of the things we saw in our last video, or our last section, was that in general, matrix multiplication is not commutative. We saw that when we tried to multiply two matrices that were different dimensions, and it just didn't work. So, kind of reviewing that again, if this is A and this is B, A times B gives me a 2 by 2 matrix. But B times A gives me a 3 by 3 matrix. So in general, matrix multiplication is not commutative. But that's in general. And let's take a look at this, because this is kind of a special case here. And let's see what happens there. So we'll go to our graphing calculator. I'll show you matrix A, and then matrix B. Both of those are in there. And now let's take A times B and see what we get. So, all right, here's matrix A. And then you don't need a times between these if they're written adjacent to each other. The calculator knows that they need to be multiplied. A times B is 1, 0, 0, 1. Okay, interesting. Let's try it the other way. Let's try B times A. Second matrix, this time B, and then A. A times B and B times A. Hey, wait a minute. They're the same thing. So that's weird. And that one thing is what's called the identity matrix. Now, if this happens, if A times B and B times A give you this kind of a matrix, then A and B are inverses of each other. So that much is stated down here. It's a way to verify that A and B are indeed inverses of each other. It is to multiply them together and see if you get the identity matrix. Now, just to let you know, we don't have to just deal with 2 by 2 matrices. You can deal with the identity matrix of any size. So for instance, I'll call I3 a 3 by 3 matrix like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. That's I3. Does anyone want to take a shot at what I4 is going to look like? I4 is again going to be a square matrix, 4 by 4, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, and so on. You can have identity matrices of any size. Now, a good question is, well, why do they call that the identity matrix? And let me give you a good answer. Let's go back to our calculator. And I put the identity matrix in matrix C for me. So let's just pull that out. So 3, there's our identity matrix. Let's take a look at what happens if I multiply matrix A by C. So second matrix, enter, that's matrix A. And I'll just hit the times key and it'll multiply my previous answer by matrix C. And that's the third one down. Oh, and I get the same thing back. If I multiplied matrix B by matrix C, the same thing would happen. So let's clear this out. Let's take a look at matrix B. And now let's take a look at B times C. So matrix B times matrix C. I actually didn't need to hit the times key there. And the interesting thing is that it doesn't really matter what side I put C on. Usually matrix multiplication isn't commutative, But the identity matrix is commutative. It will multiply on either side of your matrix and give you the same thing. So C times B, there, same thing. So that's kind of a nice property of our identity matrix, and one that we're going to kind of use. Now let's go back and remind ourselves how to write a system of equations as a matrix system of equations. We're going to do it with this one right here. So you may remember that you're going to start out with your matrix of coefficients. That's going to be 3, 5, 5, 8. And then your matrix vector or your column vector is just going to be the variables x and y, and then -4 and -7. So that's our matrix system of equations. AX equals B. Now, we're going to solve this by finding the inverse matrix. And here's what the inverse matrix is going to do. The inverse matrix is going to allow us to solve this system of equations and get x by itself. And it's going to do that by multiplying on both sides of the equation, and one of those sides is going to cancel each other out. Now, in kind of theory, this is not much different than 7x equals 21, what we're going to do here with this matrix system of equations. And you don't have to take notes on this, but I just want to remind you of what you could do to solve this. Now, most of you already divided this by 7 and got x equals 3. That's fine. But let me write it a little different way. I'm going to multiply both sides by the reciprocal, which is 1/7. Now on the left-hand side, 1/7 times 7 gives me 1. On the right-hand side, 1/7 times 21 gives me 3. And then 1 times x is just x. So there's my solution. How does that relate to matrices? Well, we're going to do the same thing except with matrices. Remember when we're working with this, this is no longer just a linear equation like 7x equals 21. This is a matrix equation. Let me put a little x here as kind of a reminder. Now what I'll do is I'm going to multiply both sides of this on the left-hand side by the inverse matrix. And let me just see if this pen is feel like cooperating today. Yeah, I think it will. So it'll be A inverse multiplied on the left. Now I have to be careful to multiply on the left because matrix multiplication in general is not commutative. So if I had it on the right, it may not work. But on the left-hand side, I've got A inverse times A. That's going to give me the identity matrix. And then if I keep on going, the identity matrix times anything is just going to be, whatever it was. It's the matrix equivalent of multiplying by 1. Now the good news for us is twofold. One, you don't have to show all this step. You just have to calculate this. And the other good news is that you might not even have to calculate A inverse by hand. Now, I will show you one example on how you would find the inverse of a matrix. It's not pretty, it's not fun. Be happy I'm not making you do a 3 by 3. That's kind of ugly. All right, so let's see if we can't find the inverse of, say, this matrix here. All right, now here's how this is going to work. We're going to start off with that matrix, and then we're going to expand it. So if A equals this matrix, 2, 7, 1, and 4, find A inverse. So I'll take 2, 7, 1, and 4, And then next to it, I'm going to kind of double the size of the matrix. Next to it, I'm going to write the identity matrix of the same size. So 1, 0, 0, 1. So this is just really the identity matrix of size 2. Now I've already programmed that into my graphing calculator so that I can kind of go through it that way. But here's what you're going to do. We're just going to worry about the left-hand side of this matrix, and we're going to try and manipulate the left-hand side until it looks like the identity matrix. So I'll show you this here by hand first. And by hand, I think I would interchange row 1 and row 2. I want to get a 1 up here in the upper left-hand corner because I want to make it look like this. So that would be 1, 4, 0, 1. And then 2, 7, 1, and 0. So all I did is I swapped row 1 and row 2. Okay. Well, then what? Then I need to get a 0 here. So how could I get a 0 here? Well, I could take negative 2 times row 1 and add it to row 2. So negative 2 times row 1. Well, row 1 is going to stay the same. Negative 2 times row 1 is going to look like this. Negative 2, negative 8, 0, negative 2, 2, 7, 1, and 0. So 0, negative 1, 1, and negative 2. 0, negative 1, 1, and negative 2. Okay. Now what else? I need to get a 0 here. So to do that, I could add 4 times this row to this row. So 4 times row 2 added to row 1 is going to be 0, negative 4, 4, and negative 8. So that's going to give me 1, 0, 4, negative 7. So 1, 0, 4, negative 7, 0, negative 1, 1, and negative 2. And finally, to make this completely look like the identity on the left-hand side of this, I'll multiply this by negative 1. So negative 1 times row 2. 1, 0, 4, negative 7, 0, 1, negative 1, and 2. So after all that, I've got the identity matrix on the left-hand side, but on the right-hand side, that's A inverse. So all those tricks that we did, putting things into row echelon form or reduced row echelon form, I mean, that's where you would use them right there, is doing that, putting this in the right form so you can get A inverse. Now if you'd like, I can go through kind of quickly and show you what that would look like if you use program row ops. You want to look at it that way? What I might do for the next exam is give you extra credit if you can show me these kind of steps and find the inverse of a matrix. I don't know. That's a possibility. So it's up to you. Want me to bang through it with row ops? Okay. That's okay? Yes? No? All right. So, yeah. All right. Well, with a roar of approval from my class here, let's do it. So program, row ops, I put this on everyone's calculator, so we should be good. Select matrix. I've put this in matrix D, so I'll select matrix 4 right there. And it makes it pretty easy. So the first thing I wanted to do was I wanted to swap row 1 and row 2. So I'll pick row swap, row 1 with row 2. And then I wanted to get rid of the 2 down here. So I'll multiply row 1 by negative 2 and add it to row 2. So that's going to be a multiply row add. So that's the fourth option down. Multiply row 1 by -2. Add it to row 2. Okay. Let's get rid of the 4 here next. So multiply row multiply row 2 by 4, add it to row 1. And I'm almost done. The last step is to multiply row 2 by -1. So in that case, all I need is this third option, multiply row. So 3, multiply row 2 by -1. The identity matrix is on the left-hand side. The right-hand side is our inverse. Yay. Now, part of the reason I have a lack of enthusiasm for making you do this by hand is because it's so easy to get your calculator to do this. Are you ready? Follow me on this one. Hit the second key, then the matrix key. And I forget which one had, I think it was an A, so it was in 1. Let's just bang it out here. Yeah, that's the right one. So if I want the inverse of that, and I hope you can follow me on this, you hit the X inverse key and then press enter. And that's the inverse. Yeah, there's just not that much to it. Your calculator actually does a lot of work, and depending on the particular matrix, it could do an awful lot of work. And not everything's going to have an inverse. We'll figure that part out in section 10.6. But for now, that's the inverse. And that's beautiful, because that's going to make your job solving systems of equations a lot easier. Now, let's practice this a little bit in terms of finding some inverses. And let's see how that's going to apply to us solving a system of equations. So let me clear out all this stuff. And then this. Let's take a look back here. Let's take the time to enter two matrices, this one and then this one. So this one is what I would call an upper triangular matrix. It's upper triangular because you've only got things on or above this diagonal. So the upper triangle of this matrix. And the next one, what are the dimensions of the second one here? 4 by 4, thank you. All right, so let's enter both of these matrices. So the first matrix, go over to edit. We want to enter a 3 by 3 matrix. So 1, 9, 7, 0, 4, 1, and then 0, 0, 7. Okay, I think that looks pretty good. At the same time, I'm going to enter in a different matrix. So I'll enter in matrix B. Matrix B is going to be a 4 by 4, so kind of a whopper by our standards today. It's going to have matrix entries of 1, 0, 0, 0, and then 0, 4, 0, 0, and then let's just put in the diagonals, right? Because it's 7 and then 9. Wow. All right. So lots of things here. Let's clean this up. If you want to find the inverse of the first one, type that matrix and hit the inverse key. Now that looks kind of ugly. More often than not, WebAssign might want fractions. So hit the math key and then answer the fractions, and oh, that looks a lot more pleasant. Now, there's something interesting that you might notice on the diagonal, and that is these numbers on the diagonal are the reciprocals of what they were. For giggles, let's just take this and multiply it by the matrix that we started out with, which was matrix A. So you've got an inverse times a matrix, and guess what? You get the identity, which is what you should. All right. How about the other one? Matrix D, or matrix B, I should say. There's our matrix. If I hit the inverse key, yeah, looking kind of ugly. Hit the math key, answer the fraction. There we go. That's the inverse of our matrix. And there's a nice follow-up question to this that's in your homework. So we calculated the inverse of this matrix. Can you generalize the result to this kind of matrix? If this is A, what is A inverse going to look like? Did anyone catch that? Take a look back at our last example. So let me write matrix A or matrix B again. So for comparison, we'll have both of those kind of up on the same screen. There was matrix B, and then here's its inverse. What's the trick for this special type of matrix to get the inverse? Did anyone see that? Here, let me write it down because it's not quite showing up on the same screen. This is A inverse is 1, 1/4, 1/7, and 1/9. And then zeros everywhere else. I'm not going to take the time to write in 16 zeros or 12 zeros. Can you see the trick in getting from here to here? That's a 4. What's the trick? What kind of fraction? Yeah, it's just the reciprocal, right? It's 1/1, 1/4, 1/7, 1/9. So in this case, the answer is going to be 1/A, 1/B, 1/C, and 1/D. And the rest are going to be zeros. I'm being a little bit lazy. I'll just put big zeros there, but that means zeros like everywhere. So, yay. Nice. Now, how does that apply to system equations? We did a lot of work here. We've got this nice inverse matrix. Let's use it to solve a system of equations. Actually, maybe a couple. So if I was to write this as a matrix system of equations, it would be 3, 4, 7, 9, x, y equals 10 and 30. So this is matrix A, that's X, that's B. This is a 2 by 2 matrix, this is a 2 by 1 matrix, this is a 2 by 1 matrix. So you can multiply these things and you'll get a 2 by 1. We can solve this way. X equals A inverse times B. And that's what you have to have more or less memorized. It's the matrix equivalent of dividing both sides by A. You can't divide matrices, but you can multiply by the inverse. So let's see what this would look like for this particular system of equations. So what you're going to do is you're going to take and plug in matrix A and matrix B into your calculator. So let's do that. Let me clear out a bunch of stuff. So matrix A is going to be a 2 by 2. I have to edit that, so go over to the edit menu first. 2 by 2. And its coefficients were 3, 4, 7, and 9. Somehow I'm troubled by the use of coefficients. The numbers in that matrix are 3, 4, 7, and 9. Let's also enter matrix B. So go over to Edit, go down to matrix B. That's going to be a 2 by 1 matrix, 2 rows, 1 column, 10, and then 30. When you're done there, exit. So second and then quit. And now we need to form this product. We need to form A inverse times B. Now if you want to look at A inverse or just A, that's fine. It's not a bad idea. Second matrix A, there's your matrix A. Matrix B, I'm pretty confident we got that. So if I want A inverse, A inverse times B, matrix B, that's my answer. 30, negative 20. That's it. You're done. The hard part is just entering in the matrices. So, what are we getting? Was it 30, negative 20? Yep. 30, negative 20. That should check back in the original equation. 3 times 30 is 90, plus 4 times negative 20 is negative 80. 90 and negative 80 gives me 10. And likewise, it'll check in the bottom one as well. Ooh, that makes this consistent and independent. Just a little reminder there, a refresher on that for you. Okay. Where it really gets helpful is not so much in the 2 by 2 case, but in bigger cases. Now, you might regard 3 by 3 or 4 by 4 as being big, but in practice, people solve thousands by thousands, tens of thousands by tens of thousands, hundreds of thousands by hundreds of thousands, millions by millions. I mean, it gets enormous. Even storing the coefficients becomes a real challenge because there's just so much going on there. But let's work on something like this. Again, if you're going to solve this with matrices, then we need to write A. And if you want to, see if you can't pause the video and figure out what A and B are going to equal. A is just going to be the matrix of coefficients. 2, 4, 1, negative 1, 1, negative 1, 1, 4, and 0. B is 2, 0, negative 3. Do you want to practice putting this in here? Or yeah, I guess I'll stick with this. I so want to use Desmos because it's just so much user friendly. But we won't be using Desmos on an exam. So back to matrix. Over to edit. We want a 3 by 3 matrix. And the entries will be 2, 4, 1, negative 1, 1, negative 1, 1, 4, and 0. And then exit. Just get out of this. Hit the second button and quit. Go back in and edit matrix B. So this time matrix B is going to be a 3 by 1, 2, 0, negative 3, and bam. Let's get rid of all this stuff. Bottom line, in order to solve this system of equations, I need to find A inverse times B. So let's take a look here. Second A inverse second matrix B. A inverse times B. Bam. There you go. There's your solution. Wow. That's pretty fast. For a 3 by 3 system of equations, that's pretty fast. The one dark cloud on the horizon is um, kind of highlighted in the last problem. And the last problem for this section. So you're given this kind of a little table here, and you'd normally use this to solve a system of equations. That's implied by this kind of a problem. But they say, wait a minute. Instead of 2, 2, 3, 2, 1, 2, 2, 3, 3, this last column is wrong. So what's wrong with that last column? Well, they say it should be 2, 2, 3, 2, 1, 2, and then 4, 4, 5. So suppose that somehow or another you had this system of equations, or you had a system of equations with this set of coefficients for matrix A. Now I can tell you and demonstrate to you right away that there's a problem. Now I know we're not used to using columns, but let me just point out something here. If I add this plus this, I get this. This plus this. So my guess is because this column is a combination of these two columns, that this matrix won't have an inverse. That is, we'll try and find an inverse, and our calculator is going to give us an error. So let's see that, and that's where we'll end up today. We'll figure out the reason why, the answer to our problem, next week. So I'll keep you in suspense, right? Which is a good thing. But let's take a look at this last one, and I'll bang it out, try and get that really quick. So let's clear this. So matrix A, go over to edit, 3 by 3 matrix, I want to keep that. 2, 2, 4, 2, 1, 4. Oh, yeah, you're right. Thank you. 2 play. I don't. Man, that's really, really bad. I remember recording that. I appreciate you giving me a chance to catch it. Let's see, 3, 2, and 5. Yeah, so let's go back here. And see, I don't even have any Photoshop, so. Oh, wait, yeah, I do. So I'll tell you what. Let's do this for a second. Come back here. And bam, see, what, where was it, 3? Yeah, okay. Yeah, I don't know where you saw 4 either. All right, well, thank you. So I think this is right now. So let's see, second mode, exit out of there. And there's our matrix. I can just hit the inverse, and it'll try and take the inverse of its previous answer. And guess what? Bam. It says no inverse exists. So, wow, what's going wrong? How come I don't have an inverse here? Have to find out in section 10.6. So, that's it for now. Hopefully, and you should get a couple things. You should be able to set up a matrix system of equations. You should be able to solve a system of equations using matrices. Now, it doesn't matter if it's a 2 by 2, a 3 by 3, or 4 by 4. It's still the same process. And bonus points if you can figure out how to calculate the inverse of a matrix the way I showed it. You know, showing all your steps by doubling the matrix with the inverse matrix. Okay. Have a good night.